So I want to talk about coordination in software projects and also in open source ecosystems. This is kind of the agenda. What I'm really trying to do is to integrate work across several stages of my career, work that all began back at Sysmil at University of Michigan. So I'll talk a little about a socio-technical theory of coordination, which is work with Audrus Moskos, testing the congruence hypothesis that comes out of that work with some students and faculty at CMU, and move on to coordination and transparency, work with some CMU colleagues. Obviously, there have been theories of coordination for some time, and they figure very prominently in my thinking about coordination. Here are some of the primary antecedents. I want to talk just a little bit more about a couple of them. Tom Mellon and Kevin Croston's interdisciplinary theory of coordination was a huge impact on my thinking about coordination, especially the notion that there are sort of coordination problems for which particular kinds of coordination solutions are a good fit, and that match is being particularly important. And also I want to, of course, acknowledge the Olsons and the impact they had on my work. As James mentioned, I was a postdoc in their lab, wandering in sort of out of nowhere. And it kind of makes me reflect on the role that chance plays in our lives. The fact that I happened to wander into their lab, they happened to have just come back from a sabbatical. They happened to have a project going on, which was looking at collaboration and coordination among software developers, which is what I've been kind of looking at ever since. I sometimes wonder what would have happened if they'd been looking at collaboration among dentists or, or something else. What would I be doing now? I'm not really quite sure. But I think as a postdoc in their lab, I learned an awful lot about what it means to try to do science, what it means to do interdisciplinary research. And I think I learned all that from them, and I don't think it would be an exaggeration to say that things I've done since have been kind of filling in the details and applying it to a slightly different context. Okay, so with that, let me go ahead and give a very quick account of this socio-technical coordination, the theory of coordination. The idea is that software proceeds by a series of engineering decisions. Those engineering decisions establish a coordination problem because they're not independent. It would be very, very easy if each decision was independent, but they're not. They're related by a number of constraints. So if, for example, I define a particular data structure and you want to extract data from that data structure, you're constrained as to how you can go about doing that. Okay? So there are many, many kinds of constraints among the engineering decisions involved in building a product. So you can think of the network of decisions for a particular project as defining a coordination problem then that the organization has to solve somehow. They have to make all those decisions without violating constraints to have a product that actually functions as desired. So just an example of how one would account for some of the well-known approaches to coordination. You can think of modularity. Modularity is a well-known solution to addressing coordination problems. If we take the coordination problem that is a single project and we identify places in this network that are cut points, we make those decisions early. We can kind of create a separate subgraph of decisions. Or we can find small cut sets and make those decisions and separate out other subgraphs. So we have now several disconnected subgraphs where before you had one large interconnected coordination problem. So these are what we would call modules in the software world or in other worlds. And the usual way then of dealing with coordination problems of this size, if you've found problems of about the right size, you can then assign them to teams, each one to a team. And since there are little or few dependencies among the work being done by different teams, they can work independently and solve the problem. And teams have a number of coordination mechanisms available to them. They report to the same manager. They've often worked together for some time. They've developed kind of a common terminology. They're familiar often with the ways that each other work and so on and so forth. They have lots of resources to draw on. and they can solve appropriately sized coordination problems. So that is how I would describe the approach of modularity. But of course, there are many other things besides being members of the same team that facilitate coordination. Geography, if teams are located in the same place, they have informal interaction, they can resolve coordination problems much more readily. If they have a history of working together before, they can often predict what each other will do, they know how to interpret each other's actions, and so forth. Creating a chat channel, for example, or using some collaboration technology can facilitate coordination among those who are using it. So, with this view of coordination, I want to sort of look at how would you then test this by deriving hypotheses from it and empirically testing hypotheses. So here are the research challenges involved in trying to do that. First, that network structure, that decision network, decisions and constraints, how do you measure that? How do you recognize what the constraints are among the decisions in a project? Another one, how do you know what coordination techniques are being used to address the coordination issues of this project? If you know both of those, then how do you see how well the coordination techniques fit the problem? Right? So that you can sort of see that, yes, this should or should not be sufficient to solve this coordination problem. And then finally, if congruence is good, if there's a good fit between the coordination that's applied and the coordination that's needed, you should have beneficial effects. Productivity should increase, and the bugginess of the software in this case bugginess is bad, right? So bugginess should be reduced. Okay. So let's take a look at how my colleagues and I tried to address these issues. So this is the set of decisions and constraints, right, that I showed a little bit before. And we can equally well show this as a matrix, right? So simply a non-zero entry in one of the cells indicates a link between those two nodes, right? So it's exactly the same thing, just rendered here as a matrix, because it's a little bit easier to think about in terms of the computations we're going to do. Now, any realistic project has some huge number of decisions, and it's so many, and they're so often so subtle, it's very hard to kind of enumerate all of them and kind of explicitly show the dependencies among each and every pair of decisions. But the hope is that we can kind of aggregate them in various useful ways, right? Perhaps abstract or perhaps aggregate. And what we're doing in this case is we're trying to aggregate decisions up to the level of a file, the code that's within one file. Right? So you can think of a file as just kind of a collection of decisions that have been made and are embodied in that code in the file. Okay? So now we have this constraints and decision matrix shown at this aggregated level of files by files, and we can measure whether there's a dependency between a couple of files in a number of ways. We've tried a number of ways. The one that seemed most useful for us is to look at the change history of a project, and if files are continually changed together, as part of the same work item, then presumably that reflects some sort of dependency between them, or why would they be continually changed together? We don't know what the dependency is, but presumably that's indicative of some kind of a dependency. So we can extract then this data from the change history for a project. Now we need to bring people into the equation, and of course, who are you going to plug into a matrix? But anyhow, bad joke, but I enjoy it every time I show this slide. So we have decisions are assigned to people. People make the decisions, right? And so that's what makes it into a distributed constraint satisfaction problem. But again, we have to aggregate these decisions since it's not really feasible to try to list every single one, and we can aggregate them again up to the level of a file. And now we're at a sufficient level of aggregation, we can show which developers have actually changed code in which file. So it's kind of an aggregated view of what work has been done or what decisions are assigned to each developer. So Morpheus is assigned F1, F6, and F7. The record shows that he's made changes to those files, whereas lazy Agent Smith only has made changes to one file. Okay, so now we do some matrix multiplication. It's pretty straightforward. We take the matrix we just looked at, the decision assignment matrix. Then we take the decision and constraint matrix, which I showed a minute ago. And then we take, here's PowerPoint striving to transpose this matrix. We take the transpose of the decision assignment network, and then we just do matrix multiplication. And we get a matrix of people by people in which the entry shows the extent to which there are dependencies between the work done by two people. Okay, so this shows that Morpheus and Agent Smith are doing work which shares dependencies. Okay? So now that gives us what we're calling the coordination requirements. Who needs to coordinate with whom to get a particular piece of work done? Right? And what we want now is some way of measuring actual coordination that can be compared with the coordination requirements matrix. And again, this can be done in matrix format. So for example, you could record team structure in a matrix. So a non-zero entry simply means two people are on the same team. If there's no entry, they're not on the same team. Okay, so you can record the team structure in a matrix in that way. But you can also record other kinds of things like geographic location. Are they at the same location or not? You can record whether a pair of people have used chat relative to some piece of work, right? Again, as a matrix or some online discussion. So we have 4 ways of recording 4 different kinds of actual coordination or coordination activity. The next step is just to compare these. You know, to what extent does this actual coordination that's been undertaken, to what extent does that match the coordination that we computed is required for a piece of work? And we've done this in a pretty straightforward way. We measure congruence as the proportion of non-zero cells in this matrix, so that's the places where coordination is needed. What proportion of those non-zero cells are also non-zero over here? So some coordination actually happened. Okay, and this is showing perfect coordination. That would be a 1, proportion of 1, because coordination happened every single place it needed to. If some of these entries were blank over here, it would be less than 1. If there were entries here where there's no coordination needed, we just ignore those because they're presumably something incidental. Okay? So if you're with me so far, then the next thing we did was to take data from a company that produces one product. It's a software company in Pittsburgh. They had, let's see, 8 teams at 3 locations, I believe, 114 developers, all working just on one product. And so we had several thousand work items, right, from this company. And we had a number of bits of data about each work item, including how long it took to complete that work item. So what we did is to construct a regression model predicting the time to complete the work item, okay, including a number of control variables that would obviously affect the duration. So for example, you know, how much programming experience the developers have, what was the size of the change, is this something that was complained about by the customer, which presumably would give it a higher priority. So we have a number of control variables that would impact the length of time it would take to complete this piece of work. And here are the 4 kinds of congruence. These are the different, measuring the match between the needed coordination and the actual coordination on those 4 different kinds of coordination activity. Structural congruence basically means if that's high, that means that the people you need to coordinate with are on your team. Okay. Geographical congruence means basically the people you need to coordinate with are at your same location. And these are 2 different kind of communication channels. And high congruence there means that the people who need to coordinate according to our computations are the ones who are actually involved in chat or online discussions. Okay? And what this regression model is showing that each of these factors has a negative beta weight and is a statistically significant predictor of the length of time it takes to make this modification. And so all of those we think that means that more congruence means shorter time.
Yeah, that's what you mean to say. Sure.
Okay, shorter time. Yes, thank you.
I was puzzled about the negatives.
Okay, well, just your hand going up was triggered the mental telepathy that was required. Okay. So we also, I should say, this was on that one company. We also replicated this study on data from another company, completely different kind of product. This was a very large company. It was a small division within that company, and got essentially the same results. It wasn't an identical model because we didn't necessarily have all these variables in the second for the second data set. But to the extent we could replicate these results, they came out the same. And we also looked at bugginess. So to compute bugginess, you need some measure for the bugginess of a piece of code. So what we did was to compute the average congruence with which all the work had been done on a particular file. So how congruent was the work that went into this file? And we assigned that value to each file. And we then constructed a logistic regression model predicting whether this file will ever be found to contain a bug. Right? And so these are, again, some of the control variables we used, how many lines were changed and so on, things that will affect the likelihood of having a bug. There's a lot of research on bug prediction, so we're able to figure those out. And again, these 4 kinds of congruence, geographic congruence didn't matter this time. And by the way, these are incidence rate ratios. They're like odds ratios, so a number smaller than 1 means a negative relationship, and greater than 1 means a positive relationship. So these 3 kinds of congruence had a negative relationship with bugginess, meaning that more congruence, less probability of a bug ever being found in that file. Okay, so we also found some other interesting things we hadn't necessarily been looking for initially, but some interesting properties of congruence. One thing we found is in that first company I talked about, the small software company, they had 4 releases of their product. So this is work done at different periods of time over those 4 releases. And if we just plot kind of the team congruence, the extent to which the people you need to coordinate with are on your team, right? You can see that on release 1, about 2/3 of the time that was true. About 2/3 of the people you needed to coordinate with were on your team. But over the releases, that dropped down very substantially to something around 1/3 of the people you needed to coordinate with were on your team. And interestingly, if we look at the online communication, like the use of IRC chat, for example, it went from a low of a little bit above 0.4 to up, 7.3 or something like that. So we saw the congruence of the use of chat grow over time. And also the congruence of online discussions kind of grow over time. So there were online discussions going on before, but over time they became more focused on those people who had coordination requirements. That's the shift that we saw. So it sort of looks like they're using these communication channels as some kind of compensation for the fact that the people you need to coordinate with are no longer so often on your team. They're using the communication channels instead. Okay, so to go back to this, what we saw as the fundamental research challenges here, the decision network structure, we used information aggregated to the level of files, and we computed dependencies based on files being changed together over time. Coordination techniques, we observed those and represented the use of those in a matrix format. Congruence, we just compared the matrices with a very simple metric. And finally, we showed for both productivity and bugginess, both of which we replicated, that there seems to be the predicted relationship between them. All right, so that is research on coordination kind of inside an enterprise, a number of teams working in companies. But something really new is emerging in very large open ecosystem, new modes of coordination. Github calls it social coding. We're thinking of it as transparency. There have been a number of terms used to describe this mode of coordination. And so we're kind of interested in how this works. The thing that transparency has, which is different from the kind of directed, deliberate coordination that I talked about before, was that in an environment like GitHub, as I'll show in a moment, the work is just exposed for anyone to be able to see and to understand and try to use that to coordinate the work. So I'll show a little bit about how that works and what we're learning about that. GitHub, probably most people are familiar with GitHub. Some people not, but most people are, so I won't spend much time on this. This is their horrifying mascot. I can't imagine this a successful company and they show this to the world. I'm not a big fan of the Octocat. But anyhow, that's what it is. And initially, I got started working with Laura Dabish and some graduate students on this work. From my point, I was just curious about why in the world this combination of social media would be useful for software development work. You know, my at the time, fairly low opinion of social media was, you know, so you want to write code while you're watching cat videos or something. Can it actually be something, is there something more useful than that actually going on? So, very, very quick overview of GitHub. Here is a profile page from GitHub. This is Mike Bostock, who's a pretty well-known developer. You can see his contributions here. So this is kind of a heat map of every day for the last year. You can see how much work he did. And I worked pretty hard here, kind of goofed off here, and sort of tailed off. I don't know what's happening to poor Mike. And you can see popular repositories that he's worked on, repositories he's contributed to. He has 7,000 followers. He's started 29 projects. Notice this asymmetry. He's following 13 people with 7,000 following Mike. This, for a project, it kind of shows you the commits. This is just the coding activity that everybody has done in this project. Then it breaks it down by person. You can see he's committed the most, and Jason Davies has committed the second most, and so on. So all this information is just available for anyone to go look at. Here is a set of forks. So if I own a project, you'll see my repository is one of these forks. Someone else can just copy it, right? So at this point, someone here has copied it. They have their own fork. It's the code that they just copy. They copy the whole repository. They can do anything they want with it. It doesn't affect the actual main repository. Here are other people who have forked the project. But if I own this, I can go look and say, well, I wonder who this is, I wonder what they're doing. I can go inspect this. What'd they do here? I can see that. What'd they do here? I can kind of see that. This person pulled in all the changes from this branch. So now they have everything that was in this branch. I can see that happened. So I can see what people are doing in forks of my project, in copies that they've made and are experimenting with. Another thing that I found remarkable about GitHub is that these projects are very highly interdependent. This is a little bit reminiscent, I think, of what Tom was talking about this morning, is that there are lots of kind of pieces of raw material, if you will, lying around GitHub. People write libraries. They write frameworks. They just have useful code fragments hanging around. There's just a lot of resources there. So today, when youngsters, millennials on down, not people from my generation who still think you should start with an empty file and just start writing some C code or something, they never start with a blank file. They start pulling together pieces. What libraries can I use here? What frameworks? How can I wire them together? And they can make great functionality much, much faster. But that's kind of the way it works these days. Much like, as Tom was describing, trying to pull together the lower level proposals into regional and global proposals. I think it's the same kind of idea. But what kind of amazed me is if you can look at various package managers and figure out what the actual network looks like of dependencies. We stuck kind of looking at one language at a time, but if we look at, I think this is all from Ruby, we take this one project, Twitter Bootstrap Rails. It's a Ruby project. It uses these frameworks and libraries. Then just looking inside one of these, this action pack, it uses all of these frameworks and libraries. And just looking inside one of those, it uses these frameworks and libraries. And this wasn't the end. I mean, you could go on. It's much more extensive than that, actually. So these projects are very densely interconnected, many of them, not all, but this is not atypical. And so if you think about what that means, if you're writing Twitter Bootstrap Rails, you often have no control whatsoever over what these people upstream from you are doing. They could easily make a change that breaks your product. You have no say over what they do. They just do what they want to do. And you have to try to keep your product continuing to work. So this is the coordination problem that we're looking at in GitHub. Right? It's basically one product using another one. And the scale of this is impressive. I don't know if you've looked at the GitHub figures lately, but this in excess of 32, I think, million projects, million repositories on there now, and something like 12 million developers on the site. A couple of years ago, I just read this blog entry, so I don't know any details about how it was actually done, but someone fitted an exponential model to the growth of GitHub and found that it was growing actually faster than that, which was kind of startling. So anyhow, this is the site. This is the coordination problem that we're looking at in this work. So thinking of this in terms of transparency, we're using, I like this definition by Bernstein, accurate observability of an organization's low-level activities, routines, behaviors, output, and performance. So we're thinking of transparency as kind of what it is that allows all these millions of developers to coordinate their work on millions of projects. Features that seem to afford transparency in GitHub are automaticity. Everything you do, basically, is just captured and recorded. Right? Every time you sort of commit some code, every time you write a comment, every time you do just about anything online, that data is captured there. It's persistent. It is possible to make some things go away, but it's unusual for people to do that. Pretty much everything that's been done and said in all those forks and all those projects is still there. And in GitHub, things are mutually visible. It's not that some people of higher power can look down and see what others are doing, but nobody can see what they're doing. It's all symmetrical, right? It's the visibility is mutual. It's just the way the site is set up. So in our work, we found developers engaging in practices that supported the flow of fine-grained information and gave developers the impression of an observing audience. Both of those, I think, are very important. So our method, using grounded theory approach, we conducted, I think we ended up with 48 interviews, actually, in 2 phases, analyzed artifacts. The unit of analysis is the coordination instance. And I'd be happy to talk more about the methods if anybody's interested in that. We have this written up. So some of the what I want to talk about is some of the transparency practices first that we observed. A couple of the really key kinds of things that people did was scouting for projects. If I'm looking for a piece of code, some library to use that does, I don't know, numerical analysis or authorization or something, I might do a search for that. I might find hundreds. I might find thousands of things that purport to do what I need. So how do I scout around and find the projects that I might really want to use from all these others that seem to be, functionally kind of similar? And we found that people do things like this. The number of people watching a project or people interested in the project. Obviously, it's a better project than something that has no one interested in it. So I just look at how many people have started, how many people are following the people who did this work, things like that, these social cues. Are there changes going in? How recent are the changes, like weeks, months, years? You don't really want to have an orphaned project on GitHub. You want to, if you're going to use some code, you want to make sure that there are people there who are taking care of it, who are going to port it to use new versions of operating systems and libraries, who are fixing bugs. If you're using that code and nobody else is taking care of it, everything becomes your problem. You want there to be a healthy community around this code, keeping it alive and healthy. So this is one way of looking at that. Are there changes? Are people still working on this? How long has it been since there have been any changes? And also then monitoring, because remember, if I'm using all of these other projects, changes down there can impact me and make my code not work anymore, so I want to kind of keep an eye on what's going on in those projects that I'm using. So things like, I want to monitor upstream. Those are things that I'm using, right? I watch this project, and that's to make sure they don't break anything, but also if they added a feature that could simplify some of my code, perhaps I want to use it, so I keep an eye on that. But there's also monitoring in the other direction. If people are using my code, I try to keep track of that so I don't break what they're doing. It's important that I can see the forks. I can see what people are trying to do. I can comment right away. So if I see somebody trying to make a change to my code that is not a very good way to change it, I can maybe suggest a better way, right? Or if they're trying to use it with something else and I don't know if that's going to work, I might run off and experiment with that and see what they want. So these are, in a way, my customers. And seeing what they're doing in the forks is my way of getting insight into what they would really like my code to do. And then, in addition to seeking information, people change how they behave. Because in this environment, you have an audience. Everybody has an audience. Everybody can see every detail of what you're doing. I've often thought it's like, imagine as if I was in my office trying to write a paper and every keystroke, people were looking through the window and looking at every keystroke. Oh, that's a dumb word choice, don't do that. It's kind of having that level of scrutiny possible. And people realize that they're being observed or that they can be observed. And so they tell us that they change how they work. And how they work depends very much on what they perceive to be the size of the audience, who's in the audience, and so on. So they strive to make their actions legible, right? So what they do should make sense to people who come in and look at that. And also to make their process accessible. So here's a quote that I think expresses both of these. I have this idea that you should be able to go through the commit message, and that should almost help you to get a feel for how the project works or what it does, or it should also be instructional as a learning tool. We had a number of inexperienced developers who said that they would try to gain skill. If I want to learn Ruby, for example, I'll go find some of the really popular Ruby developers that have maybe thousands of followers, and I'll go and study their commits. When they do something, I don't want to just look at the code that's the end result of what they've done. I want to see how did they get there. I want to see the series of commits. Well, how did they break up this problem? They might have broken it up into, say, 10 commits or something. How did they break it up? What did they do first? And what did they do next? So I start to learn not just about what the end product code looks like, but what their process was of getting there. And people tell us that's been a very powerful tool for them in figuring out how to actually code. Okay. So I think what we're seeing, to kind of summarize, is that information seeking, the fact that everybody knows all of this information is available and that it's widely being used and people are scouring through there trying to find useful and interesting things, puts a lot of pressure on developers to make sure their actions are clear. Right? Every time you do something, you're not only committing a piece of code, you're also engaging in a communicative act, potentially. And so you want to not only write good code, but you want to have a communication that's clear and understandable, where people will see why you're coding this way. So there's a lot of audience pressure on people to express themselves clearly and legibly. And that, of course, makes the information more useful. Right? There's not a lot of trash. There's not a lot of commits that don't make sense. People behave in such a way that the information is very useful, which creates kind of a virtuous cycle and results in what we're thinking of as transparency. So it's not just that the tools let you see stuff and that the tools capture what people do. There's this whole social process that's going on of being observed, trying to make your work legible, and then interpreting it and using it in various ways. So some of the things that transparency practices allow people to do is proactively managing conflicts. Instead of waiting for something to break, it makes it possible to go be very aware of what's going on in parts of the code that matter to you and avoiding a conflict rather than waiting until it's too late and something is broken. Providing opportunities to comment or intervene. If I see somebody doing something stupid in a fork in my project, I can, before they get very far down that path, I can suggest a better alternative, or I can say, here's another solution, or let me help you with this. So these opportunities to comment or intervene come very early when they could still be used. It's still helpful. Publicly advocating and rallying to support changes. This is one of the interesting things we saw, that if it's important to me that you, the primary developer, incorporate a particular change, because that would make your code a lot more useful to me, you might not care about me. But we saw examples. This one guy had thousands of Twitter followers, for example. And so he tweeted about this change he wanted to see in a repository. And hundreds of his followers plus one his pull request. And so now the original developer who didn't really want to incorporate this change is getting inundated with hundreds of people saying, hey, we need this change. It's kind of a political leverage, rallying support around this change. And very quickly then it got plugged into the project. Again, the transparency enables that because many people can kind of see what's going on. All right, but in order to get the benefits of all of this, you have to solve kind of the fire hose problem, right? Because remember, there's 30 million repositories and 12 million developers, and it's growing very, very rapidly. How do you make sense of all of what you're seeing? Because a huge amount of information. So there's lots of information. Some of it is meaningful. A very small amount of it probably is what you really need to see. So what we wanted to do is to delve a little bit more deeply into understanding how developers make some particular key decisions. How do they sift through information? So to take this whole set of decisions and constraints and just kind of focus in on a couple of kinds of decisions. And in particular, we looked at the decision to use a project, because that's a very important one to you over the long term. You're developing a relationship basically with the people who maintain that, and whether to contribute to a project. So I make a change in I fork your project, I make a change so it becomes more useful to me. Do I bother to send that change back to you in the form of a pull request, as it's called on GitHub? I'm requesting you to pull my change into the master project. And it's work to do that. Making a pull request itself is easy, but I know perfectly well that you may not be happy with my first attempt, and I may have to do some more work on this, and it may take a while, and so on. So there's a cost to that. So these are two of the key decisions that we tried to focus in on to understand how people reason about them. And we ended up using signaling theory as a very helpful lens. Signaling theory, which comes out of both biology and the business world. People may signal in the labor market, for example. I may obtain a credential, which enables me to signal my value to the labor market, so I might command a better salary. But the idea of signaling is that the attributes we care about are often not directly observable. Okay, you don't know necessarily, by looking at me, you can't tell, am I a good software developer or not? It's hard to say. So we often infer the existence of these hidden attributes from the visible information we have around us. Well, what can you see about me that might lead you to infer that I am or am not a good developer? Well, I'm not dressed appropriately. That's one obvious problem. You would not expect me to be a good developer. So the relationship between a signal and an attribute can vary. Signals can have different levels of reliability. An assessment signal, we have to possess the attribute to be able to produce the signal. So if Tom here were to jump up on stage, take this whole podium and hoist it up in the air, we'd say, yeah, he's pretty strong. Okay, because you can't do that unless you actually have the attribute of being very strong. On the other hand, if Tom on his CV, I don't think this is here, tell me if I'm wrong, but if he said, I am really, really strong, that's just a conventional signal. He could be lying. We don't know if it's the truth or not, right? Conventional signals only have meaning to the extent that we have norms that enforce telling the truth, right? So if Tom were putting false things on a CV, we would find out and Tom would be embarrassed because we have a norm that you shouldn't do that. Your CV should be pretty reflective of what you've actually accomplished. But that's a conventional signal because it has meaning only because of our conventions and the way we enforce them. Okay, so different kinds of signals. So applying this to GitHub, we're asking this: what kind of unobservable qualities do developers infer when using signals to perform key tasks? What is it they really want to know about these projects? What signals do developers use to infer these unobservable qualities? How do they use the information they see to infer these things? And finally, what are the strengths of the associations of signals with task outcomes? I'll talk more about that in a second, but based on interviews we did, it becomes clear that if what the developer told us is in fact the basis of their decision making, and if that's generally the basis of decision making, we should see certain associations between outcomes of the decision, like projects that get used, and signals that they say they use as the basis of that decision. Okay, so I'll show more about that in a second. All right, so we're basically used the same interviews as in the previous study, but we coded now 75 instances of decision making from this set of interviews. And that was in a qualitative phase, and then we had a quantitative phase where we derived predictions from these qualitative results, and then attempted to test them on a much larger sample, looking at kind of actual behaviors like actual using a project, for example. So it turns out, just to be very terse about some of the results, we have a paper under review if anyone's interested in learning more about what we actually did, but there were three kinds of qualities for each of these decisions. There were three kinds of qualities that developers always seemed concerned with. One is they wanted to know something about the project working dynamics. How do people go about their job? What's it like to work on this project? They needed to figure out something about the personal utility of whatever it is. What are going to be the costs and benefits to me of making use of this or of taking this action? And finally, something about the project community. Is it strong? Is it vibrant? And so on. So for the decision about whether to use a project, all right, the kind of project dynamics that people were interested most was kind of project liveliness, as we would call it. They're trying to figure out, is this thing still ongoing? Does it still exist? Does it, have people contributing to it? And they would talk sometimes about things like the commit velocity, how fast are commits coming into the project, commit volume, how much code have people actually committed to this over time. For personal utility for use, they're very concerned. Obviously, they're also concerned about, does this do the kind of stuff I want, right? Is this actually a function that does numerical analysis or whatever? But within those that they're trying to select from, that's what we're kind of looking at. They're looking at project maturity. Is this ready to be used? Is it ready for prime time? Or is it just something that somebody kludged together? So they talked about, project actually has versions. I've declared that this is version 1. That kind of means that I think it's ready to go out there and somebody might use it. Or does it have more versions than that? This is now version 4. It's much more mature than version 1 was. Has there been a whole lot of recent code churn? That's a little bit worrisome. Why are they changing stuff all of a sudden? Does that mean that it's going to change out from under me if I try to use this? Personal utility, also ease of use. How much work am I going to have to do to actually pull this in and use it? Some projects have lots of downstream dependencies. You may have seen it. To use this library, you also need to install this other library and this framework and something else. If I have to install all that just to use the code, it's going to be a lot more work for me to get all that running. So having more upstream dependencies is bad from an ease of use point of view. And finally, community evaluation. Has the community expressed interest in this? So this is along the lines of the quote that I showed. How many stars does this project have? Stars, think of it as kind of a like for a GitHub repository. I'm voting for this. I think it's meritorious. I think it's interesting. So what we found, actually, in doing a regression to kind of predict use, project use, was that many of the things that we predicted had kind of the results we would expect. So the commit volume, if there were lots of commits, it was much more likely to be used. Commit velocity made it much less likely to be used. So if there's a lot of commits going on right now, a huge number going on right now, people don't think it's quite ready to be used yet. Versions had what we expected. Recent churn had the expected to be affected. What was interesting about all this is stars seem to have no impact at all. The number of stars on a project had no impact on whether it was actually used or not. So to harken back to conventional signals versus assessment signals, lots of code churn, well, that means things are changing, right? I mean, that just indicates what it indicates. And for the rest of these as well, but stars is a purely conventional signal. I just put a star on this, and by convention that means I think it's cool, but, and people say they use that as part of their decision criteria, but when you look at what actually predicts use, this has no relationship to use. And now looking at for contribution, whether I'm going to make a contribution to this project, again, is the project responsive? You know, so if they get a pull request, how long does it take them to deal with that? Accessible contribution opportunities. Do they have, is it obvious what I could do to contribute to this project? Do they have, like some of the projects have beginners lists of, you know, tasks that you could take on as a newbie. Here we're looking at project versions and project issues. If there are versions, it's kind of clear when you can contribute, you know, and if they're coming up on a version, there are lots of bugs that need to be fixed. Does it have issues? Do they use an issue tracker? And are there open issues there that you could go work on? And community evaluation, is my contribution to this project actually going to benefit anybody? If it's not, then I'm not going to bother. So we're thinking, again, if the project has a lot of stars, that might entice me to be more likely to contribute to it. Or if it has lots of downstream dependencies, lots of people are using this project, that might cause me to want to contribute to it. Our results here are much as expected in terms of time to close, project versions, issues, and so on. Stars doesn't predict anything, again. And also, somewhat surprisingly to us, downstream dependencies doesn't indicate, so that also does not apparently have the impact of indicating an audience for your change, that you're actually going to benefit somebody. Okay, so I think the explanation for a lot of these non-findings or the misalignment between what people said and what apparently they actually do en masse has to do with the difference between conventional signals and assessment signals. So I've talked about socio-technical coordination, in which we view the technical work as defining a constraint satisfaction problem that the organization has to solve, and there are several ways of doing that, and coordination in transparent ecosystem. Interestingly, one of the major differences here is the work tends to be asynchronous in these environments, right? So it's not coordination of simultaneous ongoing work, it's coordination of I have to deal with what somebody has done before, and then I do something, and somebody has to deal with that. The fact that actions are communications, and the signals, people are using information they can see as signals about the hidden qualities that they actually care about. So what some of my students are doing, trying to figure out ways of creating better and more visible signals. Now that we have some understanding of what the invisible properties are people care about, can we find ways of computing those things more easily and making those more visible? And also, I'm very interested in digital artifacts beyond software. If we think of some huge design space of people collaborating on digital artifacts, which would include Wikipedia, which would include Github, which include things besides software, on Github, interestingly, people share and modify 3D printer files. They write books. Right? And so if you find a mistake in a book, you don't just write to the editor, you make a pull request. You fork it, you fix it, and then you send a pull request back to the author. There was an article in Wired magazine written using GitHub, and then there was a meta-article about the process of writing an article on GitHub. We found a group of people who do annotations on Gregorian chants on GitHub. So I'm really curious about what is the whole possible space of these collaborative environments for digital artifacts of all kinds, and what are the options, and how do you know what is a good fit of a set of features to a particular community and kind of collaborative artifact.